Welcome to this keynote on artificial intelligence sensor for liver diseases and for the calibration of time interleave ADCs. I am Dr. Shahzad Saleem, working as assistant professor at the Department of Electrical Engineering at FAST National University of Computer and Emerging Sciences, Islamabad, Pakistan. Here is a brief outline of my today's talk. So as we know that in the present age, artificial intelligence is transforming the way we live, work, and interact. And from age-old medical expert systems and intelligent search engines to intelligent chatbots and predictive models, the AI practices are growing rapidly everywhere. Professor John McCarthy, a professor of computer science at Stanford University, once defined the AI in the simplest manner as the science and engineering of making intelligent systems, where these intelligent systems can be in the form of software, hardware, or a combination of both. There are 6 key elements of AI, and in particular, I am focused on computational intelligence element, where we focus on utilizing and driving value from data with the help of data science techniques, which includes various scientific methods, processes, algorithms, and systems. And we utilize 2 particular machine learning aspects. One is supervised machine learning, and the other one is unsupervised machine learning to make inferences from our available data. So our first application of today's talk is artificial intelligence sensor for liver diseases. This is based on a supervised machine learning method. According to World Health Organization, viral hepatitis is the 8th highest cause of mortality globally. And usually the patients of viral hepatitis remain unaware of the disease for a longer period of time, and that can lead to several health complications in their case, or even it can prove fatal in some cases as well. Now, to detect liver diseases, there are 2 methods. One is the blood test, and the second one is the imaging technique. Unfortunately, both these techniques are unable to detect the disease at its early stage. Therefore, to address these issues, we propose an artificial intelligent non-invasive sensor which can help us in measuring liver stiffness and scarring to diagnose viral hepatitis at an early stage. So here is the design methodology adopted by us. Subject is observed with the help of a flat vibrator and ultrasound sensor. The acquired values are passed to a microcontroller such as an Arduino, where these values are digitized, and the data is passed to a trained model which has been trained using a particular machine learning method. And the model is capable of evaluating the data, and based on this, it is going to decide whether the subject is suffering from liver diseases or not. We have designed a prototype sensor, as can be seen on the left of your screen. And on the right hand side, we have also evaluated the performance of this device with the help of different machine learning classifiers. In particular, we were able to achieve up to an accuracy of 95% and a precision of 98% in this case, with the help of a machine learning method known as decision tree. My second important application of today's talk is calibration of time interleave analog to digital converter. A time interleave analog to digital converter utilizes channel ADCs in parallel to achieve a high sampling rate of Fs, where each channel ADC is operating with a sampling rate of Fs over M. Here we can see a system model of a time interleave ADC where an analog input is processed by a chain of ADCs, and we are able to achieve a digital output at a sampling rate of Fs samples per second. On the right of your screen, you can see the working principle of a time interleave ADC. Just focus on these blue lines. I have selected as an example a 4-channel ADC. Now, how does an ADC works? Time interleave ADC works. So we start with first ADC, ADC 0, to acquire the first sample. Then we acquire the second sample at Ts second. We acquire the third sample at 2 Ts second with the help of ADC 1 and ADC 2 respectively. And then we acquire the fourth sample with the help of ADC 3 at time t 3 Ts. And this continues in a similar manner unless we are done with all the data. However, in the case of time interleave ADC, each ADC in this array may differ from each other in the case of certain characteristics. That leads us to experience some gain errors and timing offsets in the operation of this device. Now focus on these red lines where we can see that instead of acquiring the first sample at time t equal to 0, there is a timing offset that led us to acquire this first sample at R0 Ts, and we experienced a scaling of G0 in this case as well. Similarly, the second, third, and fourth samples also experiences offsets of R1 Ts, 2 Ts, R2 Ts, and R3 Ts respectively, and they also experience certain gain errors as G1, G2, and G3 as shown here. So this leads us to experience a decrease in the performance of this device, and our digital outputs will contain errors. To cope up with this issue, the method adopted is to put a block in front of a TI-ADC, which is known as a calibration block, and which is used to correct these mismatches such that we are able to generate a digital output which is free of errors. In this regard, there are two calibration techniques. One is known as foreground calibration, and second one is known as background calibration. In the case of foreground calibration, normal TI-ADC operation is halted for a certain amount of time, and a known signal of a particular frequency, amplitude, and phase is passed through ADC to measure the output. In this way, we are able to gather information such that we are able to identify the mismatches present in the digital output. In the case of background calibration, a digital block is put in the background, and it works in parallel with time interleave ADC normal fashion. So it helps us to generate the correct samples at the end in the form of a signal x hat of n. Now, both these blocks have a drawback. Number one, the foreground calibration requires us to halt the operation of TI-ADC for a certain time, whereas background calibration may take quite longer time to start generating the correct digital output. To cope up with these issues, we propose a neural network approach that can be used to generate a neural network function which can instantly give us the estimates of the mismatches, timing and gain mismatches, or timing offsets or gain errors, and we can utilize those values to generate the correct output. Here we can see that we utilize some known values of the gain and timing errors, and these values are can help us in training a neural network model which at a later stage can become a block in front of a TI-ADC, and it can instantly estimate the errors, gain and timing errors present in the digital output. And we can utilize those values to reconstruct our correct output. Concluding my talk, I have presented a brief overview of an artificial intelligence sensor to detect liver diseases and calibrating a high sampling rate time Interleave ADC. We can utilize such solutions in designing digital processing circuits and systems which are capable of directly sensing or estimating desired parameters. In the future, we are working on the design of a flexible sensor in the form of a wearable device, which will be utilized to detect liver disease in a patient. Furthermore, we are also working on different AI models to further improve the performance of the calibration method using AI techniques. Thank you very much for your time, and I'm looking forward to your questions.